Okay, so let's look at the following example. This following example, it says it can be shown that the function 1 minus x to the 6 over 6, this would be less than this 1 x sine x all over the quantity 2 minus 2 cosine x, which is less than 1. This holds for all values of x close to 0, and it wants to know what, if anything, does this tell us about the limit as x approaches 0 of this middle function that we looked at. First thing I would always do is I would do my direct substitution, and I would see, do I get some number out of here? Unfortunately, if we go in here and we plug in 0, wherever we see an x, we get 0 times sine of 0 all over 2 minus 2 cosine of 0. When we recall, sine of 0 is 0, and we have 0 times 0 is 0. And this is all over 2 minus 2 cosine of 0. Cosine of 0, recall, is 1. So we have 2 minus 2, which is 0. So we do get that indeterminate form in between. And we can try to manipulate this using some of the tools we used before, try to factor. I don't see any factoring that would help me right now. We could probably try to multiply by the conjugate, see if we see any trig identities to help us. But because it gave us this information above, and we can find the limits of the functions on the left and the right of this one that we're trying to find, we can use that sandwich theorem. So let's look at the limit as x is approaching 0 of 1 minus x to the 6 over 6. This would be less than the limit, which we're trying to find, as x approaches 0 of x sine x all over 2 minus 2 cosine of x, which is less than the limit as x approaches 0 of 1. Okay, so let's just do direct substitution on the one on the left. If we go in and we plug in 0 wherever we see an x, well, we would get 1 minus 0 to the 6 over 6. It's less than this limit over here as x approaches 0 of x sine x all over 2 minus 2 cosine of x, which is less than. So recall, when you're looking at the limit of a constant, that's always going to equal that constant. Again, that constant, a line, is horizontal. Any value you go, you're always going to get that same y value. So this we're going to get back as 1. And so we have this 1 minus 0 to the 6 over 6. 0 over a number is okay. It's not okay to have a number over 0. And it's not okay to have 0 over 0. But 0 over a number is okay. So this is just 1 on the left. Well, if 1 is less than this limit, and that also has to be less than 1, we have to, in order this to be true, actually the limit in the side would have to equal 1. So it's possible that there's an open circle in here, but this would be going towards 1. And we again can talk about and say this because of the sandwich theorem. Okay, so we just finished with limits on 2.2. We're skipping 2.3 for now, coming back a little bit later, maybe next week or the following week, but soon. But we're going to jump into 2.4, one-sided limits. So when I talked to you guys about limits, looking at them graphically, we did look at one-sided limits. And so just recall that if we're looking at a one-sided limit, so the limit as x is approaching a, and I want to know what's happening on the left-hand side of x equals a, values of a that value of x that are smaller than a. This is how I would write it. If I was looking at the limit as x is approaching a on the right, remember I put that plus superscript of f of x. So this is left-hand sided limit. And the other one was the right-hand side limit. So looking at values close to a, but bigger than a. The other thing we said, left and right-hand side limit might give us different values. And if that's the case, maybe there's a jump in the graph at that value. Then we say that the limit itself does not exist. So the limit as x approaches a of f of x exists if we can show that the limit as x approaches a on the left is equal to the limit as x approaches a on the right. Okay, so sometimes it's important to look at these left-hand side limits when we're dealing with with functions which are piecewise functions. So recall, piecewise functions are functions that have multiple equations, and those equations are defined depending on the domain. So for instance, let's look at the limit, or actually, before I do that, let's look at the piecewise function. Oops. Let f of x equals, I don't know, 3 minus x if x is less than 2, and x over 2 plus 1 if x is greater than 2. Let's first start by graphing this. Let me make sure I started that video. Okay, so notice there's two equations. There could be more with piecewise functions, but in this case, we have two equations. And so the first equation, right, is 3 minus x. And so what this is saying, we have f of x. We're going to choose this to be 3 minus x for all x values less than 2. So that kind of upside down a, I'm trying to get you guys used to, because you're going to go further in math, probably used to some more mathematical notation. So if I was asked to find f of -1, I know -1, when x is equal to -1, I'd have to look at which inequality would that make true. Well, it makes it true for this first inequality, for x less than 2. So that tells me I need to use this equation, and I would go back in here and I would plug in -1 wherever I saw an x, and that would give me what my y value is. So that would give me 3 plus 1, which is 4. So f of -1, I know I have a point on the graph at -1, 4. So when we're graphing these, really the thing that to be careful of is making sure that you don't use an equation if it's falling outside of the domain. So I would not plug in -1 into the second equation, because that's a false statement. -1 is not bigger than 2. So just be careful with which, when you're choosing a value of x, if you're going to plot points to graph, which equation you're plugging it into. The other thing with these piecewise equations is that we have to be careful with what's happening at the n values of those inequalities. Because even though it says x is less than 2 in both of in one of them, and x is greater than 2 in one, That tells me that x is never going to equal 2 in there. Just so I have that there, I'm going to write above here. So let's start graphing these. Okay, so for this f of x equals, another way to say f of x, remember, is y. So we have y is equal to 3 minus x. Another way to write 3 minus x, maybe, so that you can see it in y equals mx plus b form, is y is equal to negative x plus 3. So this is in slope-intercept form. I know that my slope in this case, right, is negative 1. And I know my y-intercept in this case is 3. So I know I can graph this. It's a line. It is crossing the y-axis at 3. And this is, I need to put another note to myself. This is for x less than 2. The thing is, I need to see what's happening actually at this end, again, at the end of this inequality, to see what's happening to the graph. So again, 2 is not included, but numbers to the left of this, 1.9 is included in this, 1.99 is included in this, 1.99999 is included in this. So let's look at what's actually happening when x is 2. And so if I looked at f of 2 in here and I plugged in 2 wherever I see an x, I get y equals 3 minus 2, which is 1. So I know here, this is going to be an open circle. At 2, 1. So let's just do that. So when x is 2, y was 1, it's an open circle. I know that it's extending x values less than 2. This was also a line. We talked about the y-intercept. So I could tell that this is what it's going to look like for this equation, y equals 3 minus x. So that's just graphing one piece of the equation. Again, I just want to state, do not follow this graph down further, right? If I did, that's not part of the equation I'm using anymore. This is giving me values of x which are bigger than 2. When I have values of x which are bigger than 2, it tells me I need to use the other equation. Okay, so for f of x, we have another equation, x over 2 plus 1. And we're again using this for x. In this case, this one is greater than 2. So I also notice, again, this is a line. I can write this if it helps you as y equals. We can pull the 1/2 in front of the x plus 1. So it's in slope-intercept form. My slope I know is 1/2. My b value is 1. I can't graph that point because this is my y-intercept, right? This is the point 0, 1. But my x values have to be greater than 2. So this is actually not on the graph. Okay, so I know that I can have values greater than 2, close to 2 on the right. So 2.1, 2.01, 2.001. So I really need to know what's happening at x equals 2 for this function. So for here, if I let x equal 2, again, it's not defined. If I look at f of 2 in this case, I would get 2 over 2 plus 1, which is equal to 1 plus 1, which is 2. So I know I have an open circle at 2, 2. So if I plot that, when I go to 2, up to, I have an open circle. And now just plug in values greater than 2. Or we know the slope is 1/2, so we can rise 1, run over 2. So rise 1, run over 2. And so our graph would look like this on the right of x equals 2. Okay, so that's just kind of going back into looking at graphing piecewise. You have to do it in pieces. Make sure that when you're plugging in values or you're graphing it, you're keeping within the domain of the inequality that's given for that equation. And it's always important to, even though it's not included necessarily at the inequality, it's always good to plug in that value into the equation. And if it's not included in that inequality, that in value of the inequality, then you put an open circle. If it had an equal sign underneath this, then you would put a solid circle at that point. So now with this piecewise function, we can go in and answer different questions. The thing with piecewise functions, notice that this first equation, 3 minus x, that's a polynomial. So basically the limit would exist everywhere that we plugged in. It was defined. Same thing with the second equation. If this is a polynomial, and there is that theorem that says that the limit of a polynomial as x approaches a of a polynomial is just that polynomial f of a, if it was f of x. So the only thing that we really have to worry about with limits of something existing or not existing is when these values are changing domains. And so it's important if we're looking at limits and we're seeing if it's undefined somewhere and we're given a piecewise function, where we're really concerned are the values at the endpoint of the inequality. Let me just go a little further with this. So looking at this, it says, find the limit of f of x as x approaches 2 on the left and 2 on the right. Okay, so again, the reason they're asking me this is because, again, these are the values at the end values of my inequality. We're given the graph, or we actually graphed it. And it gives us the equation. And it asked us to find the left and right-hand side limit. So I want to keep on the same page of the same work. So we're looking at the limit as x is approaching 2 on the left-hand side of f of x. Okay, so 2 on the left. So in this case, if I look at the graph, 2 on the left would be this piece that I had put in red. And so I want to see what's happening to my y value as x is getting closer and closer to 2. Well, as x is getting closer and closer to 2, on the left of the graph, our y value that we're getting closer and closer to, but not including, is 1. And if I look at the limit as x is approaching 2 on the right of f of x, well, this is what we had, or I had made in blue. And so coming in x closer to 2 on the left, the y value I'm approaching, even though it never gets there, is 2. So because those are not the same value, if it asks me to find the limit as x approaches 2 of f of x, we would say that it does not exist. And you had shown me that on a test or whatever by showing me that the left and the right-hand side limits are not the same. Questions on that? So it's possible we could have found these limits without actually going through and graphing this at the left and the right of 2. So let's look at an example doing that.